All right, thank you so much, and that was a wonderful talk, a very hard act to follow, but this is in a related field, so I'm guessing some of you will follow along. So our work here talks about a new type of ultrasound imaging system that we are focusing towards wearable ultrasound applications, and we have a very specific application in mind. However, we feel that our technique can be used in multiple areas. So I'm Biswarup Mukherjee. I am from the Center for Biomedical Engineering at IIT Delhi. This work is in collaboration with Dr. Ankesh Jain, who's also faculty at the Department of Electrical Engineering at IIT Delhi. And this work has been done by our PhD student, Deepak, who unfortunately couldn't be here today. So I'm presenting on his behalf. So at the very outset, I think I'd be preaching to the choir if I said that, ultrasound is probably the most accessible imaging technology, at least for low and middle income resource settings, right? But however, we see that with point of care ultrasound systems, still the reach of these systems has not penetrated to the depths of our society. And one of the reasons that you will constantly see when you look at large-scale surveys done in these countries, like very low-income countries in Africa, even in India and in Southeast Asia, that one of the things that people talk about is the lack of training. So ultrasound is very, very hard to interpret, right? So if I give you an ultrasound image, you will probably not be able to tell a soft tissue from a bone if you were not trained to do it, right? And apart from this, there is also the fact that these devices tend to be the size of a mini fridge, right? So tagging this along for multiple applications would be very, very tough. And even though we have come a long way, we have seen portable ultrasound systems becoming more and more popular. However, we do know that there are places where even the lack of electricity or power can be a limiting factor towards accessing these technologies. And this has been shown time and again in multiple surveys, right? So the clinical need, therefore, is a real-time, wearable, low-power system that essentially can sit on the patient's body and can be used remotely to monitor their, say, hemodynamic parameters or some other physical parameter, right? So with this motivation in mind, we found that there are several groups recently that have published a lot of work, very, very interesting cutting-edge work on developing transducers, very, very high-end transducers that look at tissue imaging using phased arrays. So this is very recent work from a group in MIT which got a lot of attention, where they call these bioadhesive ultrasound arrays that essentially image the carotid artery and so on. So these have been quite popular. And recently our group and many other groups have started looking at the use of ultrasound for real-time monitoring of muscle activity. So musculoskeletal imaging, but from the perspective of monitoring muscle activity, right? So something that you would do with, say, electromyography. As an analog, we're using ultrasound, and we call this technology sonomyography. So there are groups out of the UK, there are groups out of the US, and our group as well, which is working on this technology. And for these types of systems, the kind of transducers that we saw in the last slide may not be very appropriate, right? So these are sort of 2D imaging arrays, and we don't need such rich data in many cases. So there is a need for wearable devices that enable real-time activity monitoring, maybe perhaps with a single sensor, with in a low-power, low-cost setting, right? So with this motivation in mind, what is preventing devices like these from becoming wearable, right? One limitation is definitely on the transducer side, which seems to have been fixed to a large extent. The other aspect is we need to fit all of these electronics inside, say, a prosthetic socket like this, right, for activity monitoring. Or if you want a sports person to sort of lug this around, you need to fit all of this inside there or on a fanny pack on their waist, right? And the main limiting factor there is the electronics. So to the uninitiated, I just want to introduce you to the predominant paradigm that is used for ultrasound imaging, which is called pulse echo, right? So in pulse echo, essentially you have a transducer, which is a piezoelectric crystal, which you essentially hit with a electric hammer, right? So you're hitting it with a high voltage pulse. This is essentially sending out a high voltage transmit pulse, right, acoustic pulse that travels through the tissue, gets reflected back, and you get these low voltage pulses which have to be then multiplexed through a switch and then pre-amplified, and then you have all the electronics. And then, very importantly, what you're looking at is this transit time and the amplitude of the return signal in order to be able to decipher how far the reflector is and how strong of a reflector it is, right? So the temporal information is critical as well as the amplitude information. So the high-speed ADC plays a very, very critical role in this paradigm. And then typically you have a large array of these, right? So one of the biggest challenges here that we are using a dense imaging array, so that prevents miniaturization of these devices. We have high voltage electronics, which again prevents miniaturization. And then we have RF sampling requirements, which doesn't allow us to break the low power limit, right? However, there are many, many applications where we do not require these sort of dense imaging arrays. So for these applications, we thought of coming up with a new paradigm, which was first proposed by Richard Heiser for an application called time domain spectrometry for basically doing audiometry of rooms like these, where we have a low power, low voltage chirp generator. So this is generating a linear chirp, so which is establishing a relationship between frequency and time. So remember, we measure time as a proxy for the reflector distance. Here we are using establishing a relationship between frequency and time through a parameter called sweep rate, which allows us to transfer the time measurement problem into a frequency measurement problem, which we'll see right now. So we transmit a low voltage pulse, a low voltage chirp. This reflects back, and this reflected signal is also a chirp, but only delayed in time. However, this time difference can now be deciphered in terms of a frequency difference. And this is very commonly used in the ultrasonic sensors that robotic applications typically use, but this has not been used in medical imaging. So this frequency difference essentially translates to the time difference here. And we can use a simple mixing circuit or a heterodyning circuit to decipher this frequency difference. And this frequency difference happens to be a lot easier to decipher than the time difference because we don't have to measure time very accurately anymore, right? And by using a simple FFT after the heterodyning, we can transfer this amplitude versus delta F, or the frequency different plot, to a typical A-mode plot, which is a depth versus amplitude plot, right? So you get an A-mode image simply by doing an FFT of the unmixed signal. But the catch here is that you have to choose the sweep rate very, very carefully such that this delta F doesn't fall into the megahertz range, right? Then you're still stuck with the same kind of problems. So you have to choose this sweep rate appropriately so that this delta F comes down to the audio frequency range or lower frequency ranges. So we designed a small system for wearable applications like the ones that we had discussed here in order to be able to realize this, with the ultimate goal that we want to have an on-chip realization. My colleague Ankesh is a chip designer. So our aim is to miniaturize this to an extent that we can have a single chip that's doing, say, multi-channel measurements using this paradigm. Right, so we have the typical power amplifier which amplifies the chirp, matching circuits, and then this gets transmitted through a transducer. The reflected echo is first received by a low noise amplifier, typically as you would find in an ultrasound system, unmixed, passed through a low pass filter, and then sampled, but at a much, much lower audio frequency range. Right, so this is sort of the schematic diagram. I don't want to bore you with the details, but essentially we simulated and looked at the low noise amplifier and the transmit amplifier. We designed this to have a fairly large bandwidth for most applications, for musculoskeletal applications. We also made sure that the voltage noise is low enough for our applications. We designed the amplifier using the mixer using standard topologies, using a doubly balanced mixer topology, which gave fantastic results. And then we did some very simple pulse echo, reflector-based tests to see how do we optimize the sweep time, right? So the sweep parameters in order to get the best image quality for our applications. So here we look at the SNR of the signal, the unmixed signal, and then we look at the CNR of or the contrast to noise ratio of the A-mode signal, right? And we find that around the 20 millisecond mark, which is around a frame rate of 50 hertz, we get this nice peaking of the SNR and CNR. At the lower end, this drop is primarily due to the fact that we are not depositing enough energy in order to retrieve signal back. At the higher end of the spectrum, we see a drop primarily because of the limitation of our systems. The bandwidth limits the resolution of the system at this point, right? So this is work with, in collaboration with Professor Siddhartha Sikdar, who was also my postdoc supervisor at George Mason University. Here we look at how we can use this system to predict gestures and motions. So we here have an M mode image. So this is a mode image stacked over time. So this is time on the x-axis and depth on the y-axis, right? So this is the skin surface, and this is, say, about 4 centimeters into the tissue, right? So we can see these myofascial interfaces, perhaps even the radius and the ulna, and this is a transducer placed on the forearm. So as we perform different gestures, like say tripod, rest, power grasp, and then different other gestures, we see these differing patterns emerge in a 4-channel system, right? So each of these are 1 channel each. So we see these different nice patterns emerge. And when we pass this through a simple, say, nearest neighbor algorithm to try and decipher whether we can see these differences through a machine learning algorithm, we find that up to 9 gestures can be very easily deciphered using a very simple classifier system with very high degree of accuracy, which provides promise towards wearable muscle activity monitoring. So here is a video of, let's go click. So this is a wearable transducer with 4 channels. This is again work done by our colleagues at Mason. So this is, so here you see that the motions are being deciphered in real time and then transferred over to a prosthetic hand wirelessly. So we have a demo of a similar system based on pulse echo paradigm, and the live demonstration, please do visit. And we also have another poster by my student Annie, who's in the audience here, and my student Manikandan, who's going to handle the live demonstration. So if you want to see this technology in person, please do visit our live demonstration. With that, I'd like to conclude. If there are any questions, I'd be happy to take them.